In this formula, this operator and the operator that appears here have an explicit expression as a convolution with the kernel. We are not going to use that explicit expression. We are going to work on the Fourier side. So in particular, everything that we are going to do works for the fractional adaptation, or basically diffusion operator with constant. Okay. Also, from here, but we don't even need this. Just from here, we can see that as with linear parabolic equation, we can gain some regularity. Just, for example, taking the L2 energy balance. If we multiply this by U in L2, we gain here the regular parts, one derivative. If we integrate that. Okay, so basically I'm just saying that for U0 in L2 and F in L2 times H minus 1, we get 2 in L2 times H1. So we gain, no, in summary, we have a gain of one derivative with respect to the list of data, and two derivatives with respect to the fourth. Now the question is, well, we gain the derivative, it's expected because we have here the Laplace, so it's a coordinate operator, and we want to see if we can also gain two derivatives with respect to the initial. This, let's see if we can gain more than one. This is very, very easy just from the expression of UT when the force is 0. So we want to see if we can gain more than one pair with respect to initial data. Good. So U is H R. L1 so the thing is we lower the line integrability, and then we should take more than one derivative here. We can do this in Fourier. So we have CR. And we've done this many times now. Here, we multiply and divide by the adequate power of T. So this should be 1/2 R, 3/2 R. Now, this quantity here is just bounded. So we bound it by the constant. So we have C. Now we only have time here, so this is the L2 of U0. And now we have the L1 norms. Integral of T minus R times dt. So if R is strictly smaller than 2, we get T1 minus R over 2. So R is strictly smaller. So in particular, we see that we can gain up to 2 derivatives with respect to the initial data. And the question is it also true for r equal to 2? Can we, otherwise we are somehow losing some derivatives, and if we want to obtain the result, this will not be enough. And from this bound, it looks as if it should work. No? When r is equal to 2, here we obtain a constant, so it can send work, but well, this is false because this is not converted. And in fact, the result is false for r equal to 2. One cannot gain proof of the, at least in this state. So there exists some u0 in L2 such that the solution of the equation with no force and this initial data is not in L1 time H2. And we can in fact prove something stronger, which is that this solution belongs to L1 H2 if and only if the initial data is in the Bessel space B21 C. And this, remember, this was a smaller space than H. So this one implies a one, right? So I will do the proof by I will show you a example to this first part. So this direction from here to here. I will prove this later because I will prove in general for Bessel spaces which is the better result. So now I'm just interested in the counterexample part. So if this is true, then U0 must be here. So if U0 is not here, then this is not. So we can take U0 in H2, not even. So the counterexample will be explicit. Let's assume that this is true. So we have that this norm is called I. Let me write this. This is the integral from 0. I will do it for. I will just write here for t. Okay. Just because I will do. It doesn't really matter. Okay. And now L2 norm. I write L2 norm in Fourier. So G 4. Okay. And in the end, I want to see that if this is true, this is not true. Remember the norm, this Bessel norm was the sum of the diagonal blocks in L2, so the sum in L1. And this was just the inverse Fourier transform. Okay, so I want this expression to appear here. I will split this integral in the Javier blocks. And now we can start bounding from above. Because we are in this annulus, we can bound this and also the exponential so that they don't depend on t anymore. Okay, now this part here is basically up to a constant. The diagonal blocks, no? So I'm calling this C2, which is roughly this one. And now I want to make the time interval disappear. So I will also split. Sorry. I will also split this in direct blocks from 2 minus 2p, 2 minus 2p, 2 minus 2p. Yeah. So what do we get here? Q. And I'm missing here the time integral. Oh, that's right. Yes. And again, because we are in this annulus, I can bound this from above. Okay, just some constant here. Q minus P coming from this part here. CQ square. And now take in the inner sum, we just keep one of the term, the one with Q equal to P. In particular, this is our bound. This part disappear, so we get the so we get the sum in P of the integral. And now we only keep equal to P. So this one disappears. C P squared, 1/2. We already do the integral. This is a factor of 2 to the minus 2p, which disappears with this one. So some constant. I don't know, I'm missing something. No, perfect, yes. So do the time integral, we obtain a factor of 2 minus 2p, which disappears with this one. So we get the some constant, sum in p of c. Basically, this was the definition of the B2 Yeah, so this is in the conclusion. We assume that this is really from our assumption. Okay, so this is just as a motivation of why we use this for the equations. We see that this is other things don't work out well. Now we will do it in all general vector spaces with NP and Q. So the idea, and this is for the equation or for any other equation, also for transport equation, like any equation when we work with vector spaces. We have our equation, and the idea is take the variable to blocks, so localizing frequency. And now, once it's localizing frequency, do LP estimates, integrate in time, and then add other blocks. But if we do what I just said, we do LP estimates for each block. Then solve the corresponding LP, integrating in time. And then adding J, so doing the small LP norm, what we obtain are not the original vector spaces that we had the other day. To do that, for example, here, we will obtain the capital unit LP less or equal than whatever we obtain here. Now, for example, for the initial data, no? LP this is already so what I just want to say that we obtain that if we do the LP estimate and then we integrate in time. So I want to say we are trying to do, let's say for example, the one where we report the into derivative, L1 in time estimate. Some base of the space. If we do this LP and now we do L1 time, let's say equal, whatever, and then we do the LQ, then we add all J, what we are obtaining is not this kind of spaces, but the new ones. Better, I think, I need to find the space that I will produce, and then I will do a proof in those spaces and we see why we don't want this space and we need this other one. So the space that I want to introduce that I usually denote with the theta are very similar to this one here. So this one here would be so these are the spaces we interchange these nodes.
sorting, we change the other two.
Yes, trivially sorted. There are trivially sorted and vector spaces. There is no line there. No? Yeah, so you can change the view with that.
And now the last two.
And now the last one. And in fact, these spaces, you can also have these kind of spaces with trivially sorted. Basically, the only point here is that you are iterating time before doing the representation. And in the first proposition I will do for the equation, it just appears naturally when you have to do this. But if you don't do this, you have the same problem as we were having with the solid space. Sometimes there's something just the way I define them here. If U is bigger than rho, then we can relate this to the typical space. So Q is bigger than rho, then we have that the Hilda spaces are bounded by the non-Hilda one. And so this is the case that we're interested when this is not. Yeah, this is the case that we're interested in. So maybe if we keep this space, we work with this space, we don't have control, but maybe for this one we have. And if you look at this inequality, for example, you put rho equal to 1, then all Q's here except 1 satisfy this condition. And the L1 in time is the one that allows us to gain the maximum today.
So that we get two derivatives in this range.
Yes, yes. So the reason in these spaces, everything works for the initial data and for the force and for all P and P. For example, also classic result for the equation, no? I think from at least from the 60s. So for the initial data, I already showed that it was not possible to closely solve it for Lessa or in Felder. Well, for Felder, I didn't show, but the same. So in this case, you help time. Let's say solid, for example. This is true for all P bigger than 1. But for P equal to 1, this is 1. And one can construct counterexamples similar to the one for condition. And the same is also false if you put here evidence. The case P equal to 1 for it. And the classical proof of this statement, although I know from Rudolph, as many people one of them in 2001 also. He used the maximal function, and that's why it equals 1. Anyways, okay, so let's prove gain of regularity in this. So before doing the proposition, I use the lemma, which is to see how the heat semigroup works when you have localized frequency. Okay, so this is similar to Bergstein's inequalities the other day. This is saying that if you have a function which is localized on the Fourier side, then the heat semigroup is just multiplying by this factor, which reminds what one has in the Fourier side, no? Instead of the frequency now, we obtain factors of the scale. And the proof is short and it's almost the same as we did the other day for Bergstein's inequality. So because we have this supported in annulus, then we can consider another compactly supported function in an annulus bigger than this one. So let me just write C containing C, so that C is 1 ounce. And then we can write all this. And again, as the other day, I can just do it for lambda equal to 1 and then scale for k on this. This is so take inverse Fourier transform, do LP of the convolution. So the only point remaining is to show that the L1 of this kernel is bounded by an exponential. And the point, of course, is that we have here this supported on an annulus. So this annulus, G is just comparable to a constant. This last part here is just right what we have. So this is inverse Fourier transform. let's call this KT. So to prove that this is in L1, like we did the other day, we multiply by this quantity, KT. And now when we put this inside, this here multiplying by x is the same as taking derivatives in chi. So this is identity minus lambda d. Then we integrate by parts. And when we integrate by parts, here, every time that we hit two derivatives, in the end we have, we will have this multiplied by the exponential and powers of the numerator, because we are in an annulus, and this is bounded, we obtain the result. Okay. Basically, like same tricks as we have been doing. So with this lemma, I can prove the proposition. With these conditions, then the solution to the equation satisfies on here one has to be very good. So in particular, if we put row 1 equal to row, we see that we are getting here this today. Okay. And the proof is very short, so just take the sheet equation and apply this. So let's take the blocks. So everything here are Fourier multipliers, so they just this. Now I use the lemma. Yeah. So from what we were asking for the about this definition, if we stop here, and we now take the subspaces, for example, I will do one particular case with all the coefficient simpler than this, and we take E2 so that we are in Taylor space. Then here we would have say that we want to do the C alpha fx and get into the derivatives. And let's just keep the distance here. Now I sum in J because we are in header instead of summing in order. So it's the spring in J. And later we take the LP from the outside. So if we do this, the problem is that the supreme of this quantity here is so this blows up and so this doesn't work, but it's almost working. And instead of doing this, yeah, I can delete the general truth, but if at this step we iterate in time, we keep this something. Like the integral in time of this is just bounded by 1. See here, we take the L row north in time. Okay, so here we are in the L row 1 north, we can integrate. And the second term is the convolution. So I take the L row 1. The part we take it again. And here the exponents come from the convolution. So here this is the L row 1 norm that we were taking. We split it in L row and L. However, this concludes the results. Now, put the S derivatives and take the L norm. I'm going to take here 2jx. Yes. Now this factor of 2 to the power 2 over rho 1 to the other side. What remains here is 2j. And this is this is the language. Now the exponent match. Here we are obtaining the s minus 2 plus 2r for the point. Well, just another comment. So, okay, I think this is nice to listen that the proof is kind of elementary or it's more or less easy and everything works well in the unit spaces. But this does not include the classical result that I mentioned before for LP here. The one I mentioned that the solution to the force heat equation with zero initial data in LP time, for example, C2 alpha. And this is true for all p different than 1. This result is not included in this chain. Just to mention that, okay, these are nice, but sometimes if you want to work with these spaces and you don't care about p equal to 1, then maybe you want something with this.
Spaces.
So it's not included from okay, so this should be a part of the index here. So yeah, so this is the LP level. So C2 alpha is B infinity 2 plus alpha. And here Q is bigger than P. So the inequality goes in this direction. So you know that this quantity is smaller than blah blah, but you don't know about this. And in fact, this is the problem for t equal to 1. This is not true, but this one is true. So now we can apply this for Navier-Stokes. So if we have initial data in any critical space like this, you can check the powers. This is in RD. Then there exist unique solutions to Navier-Stokes. So I said today we were going to prove it using a fixed point argument, so we need a small solution. So the initial data in this case of a space, such that its norm is small. Then we have a unique solution. Sorry, a unique solution. And the spaces that I'm going to write look exactly as the one that corresponds to the solution of the heat equation with this initial data. Okay, yeah. So, as I said, no, like we have in any infinity time, we don't gain any regularity. In L1 time, we gain two derivatives. Another proof of this, I just write again the lemma that I wrote in the last lecture. This will be based on the fixed point argument. And the solution written in my form. With this in mind, we had this lemma which says for X some Banach space. Then we had a bilinear form going from X to X. Then for any y in X with a small norm, exists a unique solution X, giving some both. To the fixed point equation given by. And now just looking at them, y is going to be this part here. So we will be able to make y small by choosing the initial data small. So that's why we have this condition here. And then b, the linear form. The proof of this, I mentioned the other day, is just Banach fixed point theorem. Check that this function here goes from this ball to this ball, and that it forms a contraction. So now, going back to our theorem, as I said, let's choose everything. So let X so well, the space of functions that are divergence free and living in this space. Okay. Why the solution with 0 force and this. Well, let's check that all the properties, sorry, all the conditions in the lemma are satisfied. So the first one should be that y belongs to x. And is controlled by the initial data. This I don't need to do anything. Like this is already proved from here. Just taking, if we take here, so x contains two spaces, no? If we put here L1, yeah, like basically here, if you put both infinity or 1, you have this inequality. And now the second part, we need to prove that B UV in X is controlled by the norm of U in B in X. Okay, well, the first part is just, again, using the X norm of the equation of B UV in X is less or equal, so now I'm using this part here. So the force is related to X of U and C. And I'm using the inequality both for rho 1 equal to 1 and rho 1 equal to infinity. In those cases, I can take here rho equal to 1. So in both terms, I obtain the same norm for the force depth. But this is the important thing that we are working with Euler's derivatives. I'm going to cheat a bit. I'm going to first do the estimate just in a space without the time interval. So I'm going to do this estimate. In B in Q dP minus 1. And then with whatever I take, I will do any time estimates. That is not completely correct in the sense that these are not the same spaces. But everything that I will use, which are basically interpolation and Euler, can be done in this space. So the important part of this space was already used, which was this proposition. Okay. So the first part is because I'm in the homogeneous case, this is a multiplier of 0 order. We can just remove it. and I will have to do this estimate. And for this, I use the partial differential calculus that we use the other day. So first, I write this. I don't know. This is just the let me write this dj partial j, and I will introduce the product product and the remainder. Plus, and for the remainder, I put the derivative outside. Okay, and this is because I'm doing this because for the remainder it was important that we work with positive index for the derivatives. So, I want to obtain in the end a bound with u and v in the space X. Okay? And the space X contain dpq, dp plus 1, and dp minus 1. So I will try to distribute the derivatives so that I'm always in the middle of these two spaces, so that later I can interpolate and get back to this. So here, for example, I have dp. This is the low frequency part. So I'm going to put infinity, and I can put something negative. And here I have dq. Yeah, I don't need these spaces. So, for example, minus 1/2. And then here I have dq minus 1/2 plus 1/2. So, yeah, minus 1/2. Now I use the values. So this is b. I remove the j, okay? So for all z, b dq, dt plus 1/2. Now this one derivative, so u dt q dt plus 1/2. So in both cases, I'm okay. And now I do all the other estimates, trying to get the same spaces here. This is the low frequency part. So again, I put the infinity ones here. I can put here negative regularity. And I want to go back to this state. So taking into account the same embedding as before, I put here minus 1/2 because I have one derivative. I will have 1 plus 1/2, and from the embedding, they will be minus 1 plus 1/2. So I just change this. 2 plus 1. So, and for the remainder, here we only had like this only worked when this was positive, but no matter this part here, we have derivative. So this part disappears, and now for the remainder, we can put the derivative. We can distribute the derivative without any worry. So we obtain in the end using the same embedding. The same. Okay, so altogether back to here. And I'm almost finishing now. Yeah, so I'm going to do two more steps. Okay, this is what I said that I was cheating. Now I'm going to take the L1 norm in time, and you believe that everything will work the same if we do it starting from this way. The only thing that doing it in this way, we have to write everything, and it was just a bit more annoying. So before taking the L1 norm in time, I'm going to interpolate, as I said, between the -1 and +1. The exponents before someone. So for this one, 3/4, 1/4. And this one is the other way around. Using interpolation, one of the properties of the interpolation in vector space. Now we take the L1 norm. And now we do L4 on the dual one. So C integral. Let's put this in L4. So U B -1. No, I said the other way. I want this in L4. Basically, I want the higher regularity one to appear in L1 time, because that's where we can gain two derivatives. So L4 here, L4/3 here. So 4/3, 1/3, 1. And this is 3/4. One-fourth. And we want to go back to our X spaces. So this in L infinity and this in L infinity. So and here I go back to our tilde spaces. Okay, this is false, but if we do everything, we should obtain U in L tilde infinity time B PQ dp minus 1 to the power 1/4 U L1 tilde PQ, and same for B. This is to the power 1/4. No, 3/4. Okay. And now, Henderson inequality, right? You recover. So for each one of them, no? For here, power 2, 4. What I'm saying. Okay, there is some exponent missing here, no? So for the L1 norm, so this one goes in L infinity, we get 1/3, 3/4, 1/4, and then we have the L1 to the power 3/4, and here to the power 1/4. So now, Helders, this to power 4/3, to power 4, we recover the X norm for U, and here same, the X norm for B. Okay, so all this concludes that E will be next as we wanted. It is more next than it is. And with that, we prove we have all the conditions for the lemma and the formula to prove for the system. And because mentioned the other day, this is only proving global systems. This is only proving uniqueness and global internet existence for the volume system. And if we wanted to do now local internet systems for large data, we have to modify. So basically we have to modify the fixed point lemma that I wrote, and just to show very briefly the key part. So the proposition would be, well, I didn't mention, so in the previous lemma, sorry, in the problem, in the previous proposition, in the conditions I wrote strictly smaller than infinity. So before I forget, just to say that for p equal to infinity, the theorem is not true. So in best of spaces, for example, the first one that was done, in this one, Navier-Stokes is simple. It was Turgen and Logic, and then this has been generalized for other fields. And the thing for other fields is not completely trivial or expected in the sense that in this other space, one derivative in BNO, which is a trivially sorting space. In this one, this is Hofstadter theorem. I think this is 2001. And here, Navier-Stokes is good. However, in this scale, you could say maybe this is false, but with a 2 is what it's important. And apart from that, yeah, so let me just state the result for local systems here. So for this initial data with divergence 3, then exists a positive time. All of it. And the thing is that now this time has to be, so this can be a reduction for a small time. And the only thing to remark here is that the previous theorem was, okay, we excluded p equals to infinity, but it worked for q equal to infinity. And here, this only holds for q also delta k. And the only reason for this is that b, q, s, so the smooth completely supported functions are dense here if u is not. And this is important to get at. So how does the proof of this works? Like for all local in times data in this parabolic thing, you split your problem in two. So you solve a linear problem with 0 force and the initial condition here, and then B solves the remaining part. With 0 initial condition, and the original solution U is UL plus B. So in all this, at the end, the smallness will come from this part here, that UL is this solution, and you have to prove that if you do the, for example, L1, but in fact any LP time space. So this goes to 0 as times goes to 0. So you need to prove this, and once you have this, all the rest is do a fixed point argument in this equation. And of course, from here, you will have some terms that only depend on this value that you can make it. And to prove this, you need
the second equation that we split.
Yeah.
The first this is U.
This is U, this is the whole nonlinear part. So from here, well, you obtain several terms, no one zero order, then some linear terms, and the symmetric one, and the nonlinear term. The nonlinear term is okay, so this should be V. This, you handle it as before. It's quadratic, so once that you have some smallness, this will automatically be small. The thing is to prove that the solution coming from this part is small. And this is true because UN is small if this is. And yeah, I will stop there. So on Monday, we have the last class. I will talk about the variation of Navier-Stokes, in particular inhomogeneous Navier-Stokes.